Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be talking about statistical power. Power is the probability that a hypothesis test actually detects a real effect when one exists. We're following Bess. She's an investigative journalist on a cold case she can't let go. She's still on the fraud detection case from the last video, but now she's asking a different question. Not whether the algorithm made an error, but whether it had a realistic chance of catching what it was looking for. The test cleared the traitor. Bess wants to know if that clearing actually means anything. Maybe the test was set up in a way that made it unlikely to catch a real violation even if one was there. To figure this out, she pulls up her case file. In the last video, we named two ways a test can be wrong. A type 1 error is a false positive, when you reject the null even though it's true. A type 2 error is a false negative, when you miss a real effect. What we haven't talked about yet is what determines how often type 2 errors end up happening. Because in reality, you can run a hypothesis test with the right decision rules, the right significance levels, and still systematically miss real effects if the test doesn't have enough muscle behind it. That muscle has a name, and it's called statistical power. Statistical power is the probability of correctly rejecting a false null hypothesis. Power tells you if there really is an effect out there, if the null really is false, then how likely is the test to actually catch it? Power is defined as 1 minus beta, and beta is the probability of a type 2 error. So power is the complement. It is the probability that you don't miss the real effect. A test with high power will detect a real effect most of the time. A test with low power might miss it entirely. Not because the effect isn't there, but because the test wasn't in a position to find it. Let's go back to Bess's case. The algorithm is testing for insider trading patterns. If this trader really is manipulating the market, then the question is whether the test would actually detect it. That's the power question, and it turns out power depends on three things. The first thing is sample size. More data means more power. If the algorithm has only 10 trades to analyze, then there isn't much statistical signal to work with. So even if something real is happening, the noise ends up drowning out the pattern. If the algorithm has 200 trades, however, then patterns become clearer and real effects become detectable. In this case, the flag trader had only a small transaction history in the relevant window. The sample was small, which was the first problem. The second thing that affects power is the effect size. Effect size is how large the real difference actually is, specifically how far from the null the truth sits. Blatant manipulation is the easiest kind to detect. It's a lot easier to see insider trading when the insider trader is making significantly larger returns than everyone else. Then the pattern jumps out. In contrast, subtle manipulation is much harder to see. So small persistent edges spread across hundreds of trades may take a much larger sample before they surface. In financial misconduct cases, sophisticated actors tend to keep their effects small on purpose in order to hide what they're really doing. The third thing is the significance level alpha. Recall from the last video that a stricter alpha means you need more evidence to reject the null. Needing more evidence means you'll miss more real effects, so raising alpha, which loosens your standard, increases the power. But it also increases the chance of a false alarm. You're trading type 1 error risk for type 2 error risk. Here's the core tension stated directly. On a fixed data set, alpha and beta move in opposite directions. Lower your alpha and you reduce false positives, but the beta will go up. You miss more real effects, and power falls. Raise your alpha and power increases, but you end up with more false accusations. You're trading one kind of error for another, and that trade-off doesn't go away just by choosing carefully. It's built into the structure of hypothesis testing. The only lever that improves both simultaneously is sample size. More data reduces the false positive rate and the false negative rate at the same time. That's the free lunch in power analysis. Everything else is a trade-off. Bess's case now has a complete picture. The algorithm had a strict significance threshold, a low alpha to protect against false accusations. The sample was small, and the effect, if real, was probably subtle. These three factors, all pushing in the same direction, mean the test had low power. That doesn't mean that the trader was innocent. It means that the test wasn't well positioned to find guilt even if it was there. In her article, Bess explains this to her readers. She ran the numbers on the test setup. Small sample, subtle effect with a high threshold. The results come back clean, but a low-power test that finds nothing is like looking for something in the dark without a flashlight. The fact that you didn't find it doesn't mean that it wasn't there. So that's statistical power and the trade-offs between error types. Power is the probability that a test correctly rejects a false null. It equals 1 minus beta. Three things drive power: larger sample size, larger effect size, and higher significance levels. Raising alpha increases power but also increases type 1 errors. The only way to get more power without that cost is more data. And when power is low, a null result doesn't tell you much. It might just mean the test wasn't in a position to find anything in the first place.